Okay, are there questions on that? Yes, Jonathan. Number 16. Okay, so this is number 16, and it is 10 minus e to the x. So if you want to rewrite it in kind of the format we're used to dealing with, you may want to do that. So for number 16, what I have, let me open this up real quick. Is a shift up by 10, and then it's also reflected. It's a vertical reflection, but I'll show you how in just a second. Okay, so for number 16, I have f of x is equal to, and it's 10 minus e to the x. So I would just kind of think of rewriting it as negative e to the x plus 10. So then you can see your asymptote is at y equals 10. That's your asymptote. And then what is the negative out front doing? It's reflecting it downward. So it's a vertical reflection. So this is going to be a vertical reflection. Reflect. Okay? So basically, you know what the parent shape pretty much looks like. Let me just kind of sketch it out over here. So it pretty much looks like a regular growth model going right through the y-intercept. So it's going to shift it up by 10. So I know that my asymptote is right here at 10. It's kind of hard to see, but you're right there for the asymptote. And then normally you would go up 1, but because of the reflection, you're going down 1. So the graph would have looked sort of like this, but instead it reflects it downward. So that's what's going on with that one. Does that make sense?
So then how would you plot your points?
How would you what?
Plot your points.
So this point right here is just 1 down.
The y.
That's your y-intercept transformed or translated, okay? So then what you could actually do is probably just pick a value that'd be pretty easy to find. So let's look at, what if I did e to the 0? That's going to be 1. So that would give me a 9. So that gives me another point. So at 1, I will be at 9 is where I should be. At 1, I should be about at 9. Well, wait a second. That doesn't look right. Let's see. So e to the 0 is 1. Negative 1 plus 10 should be at 9. So that's not what the graph looks like, though, is it? But you should have a point at 1, 9. So that point, no wait, I'm saying the wrong thing, is 0, 9. I'm so sorry. When I plug in a 1, let's look at what happens when I do e to the first. E to the first is almost a negative 3, right? So it's like a negative 2.78-ish. So it's going to be 10 minus 2.78. So it's going to be what? Really close to what? A 7. So it's 10 minus almost like a 3. So that's why that's not matching. So that's roughly a 7 right there. So that's how you would do that. Okay. And like I said this yesterday, but when you graph the exponential with your base of e, you're approximating, because you're not going to know exactly what the point is because they're decimals for the most part. Occasionally, like when you have e to the 0, you get a 1, that kind of thing you could graph. So, all right, let's go to the bottom part and kind of see how that looks. So here's the bottom set of answers. Okay, and I know some of you said you had trouble with the graphing, so let me do some if you need me to do them on the graphing calculator. And Gigi, do you have a question?
How'd you get the setup for 22A?
22A? Okay, so 22 talks about an accident in 1986 at the Chernobyl nuclear plant in the Ukraine released a large amount of plutonium into the atmosphere. The half-life is about 24,110 years. So you can see that is in our equation right there. Okay, and it's kind of like the example we did yesterday in class, in fact, that if you know that your half-life period is 24,110 years, then you pretty much just put in any value here and half it as the resulting value. Like yesterday we did 1.5, like we did 1 here, and we did, so that's where that information came from.
We're supposed to solve for K. Calculator and solve for it. Does anybody need to see that?
Wasn't it a half equals 2?
It wasn't a half is equal to 2. It was 1/2 equals 1. And that's the point I was trying to make to you guys. You can put in any two values here as long as you start with an amount and end with 1/2 of that amount. So in other words, I would get the same x-intercept if I did a 1 here and a 1/2 here. I could do it either way. Do you understand? I'm taking half of it over that time period. So this is the number of years that have elapsed for my decay to actually accomplish 1/2. So half of the substance would be gone. So I could start with 1,000 and end with 500. I can do it however I want. That just makes your graph a little bit more complicated when you use those bigger numbers. Does that make sense? So that's a really good question, and you will see one. You'll see one like that on the test. Okay, this is pretty basic stuff. Once you get the hang of it, you'll probably feel comfortable with it.
So how do you solve for K once you like get your
You have to graph it. So just anybody want to see that?
Yeah.
Let's just graph it then. Okay, I'm going to go to my calculator, and remember I started with 2 on this one. I have a base of V, and remember that's second ln, and then my exponent is going to be a negative, and let me double check the year, it's 24,110 years is how long it takes for it to basically decay by 1/2. So I kind of like to put my coefficient first and then my exponent. Make sure to go down, and then I would subtract 1. Now, like I said, the graph is a tad different than if I had used 1 here and 1/2 here, but the x-intercept will be the same either way. So now, thinking through this, let's just sketch it and kind of see, and I'll show you a statistics plot first. Let me get rid of that, sorry. I was running a regression earlier. So now I'm probably gonna need to play around with my windows. I definitely am. So let me see how it's set right now. So let's just start with like -10, 10. Now this one is going to shift how? Based on the function that I wrote.
down 1?
Very good, just down 1. So it's not going to be some really huge value. So I can see my asymptote. And guys, these almost always are really, really close to the y-axis here, and it's kind of hard to see. So let's go in and change our x window to like -1, 1, and then hopefully I'll be able to see it better. You still have a hard time seeing it, don't you? It is really, really close. Now, if you really don't understand what's going on here, trace it and see what happens. So let's trace it. So 0, 1 is what? It's the y-intercept, very good. Now, if I go to the left of it, I'm kind of going up, and I'm going to actually start seeing some negative y's. So this graph is actually really, really close on the left side, coming down, crossing at 0, 1, and then coming down, and the x-intercept is really, really close here. But I know it's between 0 and 1. I can see that it's between 0 and 1, because remember, that is how I have my window set. Okay, and that always works for you, because I can do second, calc, and then I'm going to find my 0, option 2, and my left bound is going to be 0, and my right bound is going to be 1, because I can see that it must cross right there. So it is very small. It's 0.0000287. So that's going to be the K value. And the K will typically be a very small decimal. Not always, but typically. Okay, so let's go back. So that was the K that we found right there. Now part B builds on that, I believe. And then what are you asked to do? You're asked to actually use that decay constant in the model and then find an ending amount. So if I start with 20, after 5,000 years, and let's see, it's starting with 20 grams. So after 5,000 years, with this decay rate that I just found, I end up with 17.33 grams. So is it decaying rapidly or slowly? Slowly. It took 5,000 years to lose not even quite 3 grams. And it's all about this decay rate being so tiny. Okay. Any others? 25 or anything?
Wait, so like to find the time in part C, would you just like, how do you look for the, like you just
Okay, you want to do that one real quick? Okay, it's very similar to what we did in part A, but now our unknown will be the time, and we'll still use that same decay rate, that same constant. And so let's go ahead and graph that, because we want to find the time that it takes for 20 to decay down to 1. So we know it's going to be a really big number, and that explains that. But let's go to the calculator and do that. So I am going to have 20 as my starting amount, my base of E, my exponent is negative, and it's going to be the decay constant of 0.0. Let me double check that. 0, 0, 0. Was it 287? Was that it, guys? Because I don't have it in front of me. Okay, thank you. 287, and then X is my unknown. And then again, it ended up being 1 gram, so I have to subtract that 1 gram over and graph that. And I'm looking for what here? I'm looking for the exponent. So I'm looking for X. It's not going to be on this window because my X's are far too small. So if I go into the window mode and I change my X's, let's just say, I'll just do 1,000,000 just to start with, just to kind of see what happens, if I can even see my graph. And then graph that. Okay, so I can see it. I still can't quite tell if it's going below the x-axis because that's what I'm looking for, right? I'm looking for where it changes from being positive x's to positive y's, to negative y's. So I could trace it just to kind of explore and see what's happening. So right now I'm at the y-intercept at 0, 19. So I'm going to go to the right. So here I am, traveling along. So what I'm looking for now, that's a really small y. I'm looking for when I have negative y's because that means I cross the x-axis. So keep going. So I'm at x of 93,617. Oh. So my window was not big enough. Now I'm at negative. So look at how big that x is. Okay, so let me change my window. Would change it for me, so that's good. So now let's just do second calc. And do you see how that says 117,000? I'm just going to use that as my right bound. So I'm going to do second calc, and I'm going to find my second calc 0. My left bound will just be 0, and my right bound is going to be 117,000. And press enter, guess. So 104,381 years is how long it took. So I don't know if the key was wrong, or let's look back at that. So roughly 100,000 years is what we said. But you guys know enough to actually find the precise amount, right? So that's where that is. So you're going to have to get comfortable with the graphing calculator and the windows and playing around with that too. Did you ever get your graphing calculator?
Yeah.
Okay, it just dawned on me. And then 25 was basically, I think if I remember correctly, we just have to use a system to solve that one. All right. So is everybody good on the new topic? Because today we're going to learn logs. We're going to start logs, okay? Today's not going to be bad, though. I think you're going to enjoy it. Now, I have a handout for you. Let me get that. And Okay. Now, I've talked about this quite a bit, about how logs seem to overwhelm some students. Don't be that student. Start from the very beginning, making sure you understand it. All right, so remember inverses. The reason we're talking about inverses is because logs and exponentials are inverses of each other. So let's just review, how do you actually find an inverse of a function? Well, this is a line, correct? The very first problem here. And remember that we learned to just, first of all, exchange x and y. X would be 3y plus 4, and then solve for what? Your y. It's inverting it. It's almost like turning it inside out. So I would subtract 4, so subtract that 4, and then divide by 3, and that is your inverse function. Now you could write that as 1/3 x minus 4/3. That would be how you'd write it in slope-intercept form. So you could do it that way as well, but that's the function right there. So just remember what inverses are graphically as well. Inverses are what? Going to be reflected across what line? Y is equal to x. So inverses are reflected across the line y is equal to x. So we'll go over that in just a second. So a logarithmic function is the inverse of an exponential function. Now, I'm going to go through the definition in just a second, but before I do that, I want to come down here and show you truly how easy the process is. I'm going to start with this one right here. Log base 3 of 81 is equal to 4. So if I cover up the 4, like literally just say, ignore this 4 right here, could you tell me what power I would need to raise 3 to get 81? It would be what? 4. So you need to start thinking about logs in that fashion. Log base 3 of whatever value. So log base 3 of 27 would be 3. So logs give you the power or the exponent necessary to accomplish something. Okay? So if I rewrite this one in exponential form, that's just going to be 3 to the 4th is equal to 81. So this is exponential, this is log form. So that's literally the basic principle that we're dealing with here. Now, if I take 2 to the 3rd is equal to 8, you all agree with that, right? The answer to a log is this right here. This is actually the answer to the log. I'm going to write this with a base of 2, so log with a base of 2 of 8 is equal to 3. So that's how you go back and forth between the two. Question? That's a base of 2. So this is how I do it. This is how I learned it. I start with my base here. This is your base of 2, correct? Of the exponential. Log base 2. So that's how the bases relate. The log has a base and it's actually lower than the rest of the equation. So it's truly called a subscript. So it's a little bit lower. And then log base 2 of 8 is 3. So the question is, what power do I raise 2 to get to 8? Well, it's a 3. So that's the basic principle. All right, so let me read this up here, and it kind of gives you some restrictions as to what values you can use. So let b and y be positive numbers, and b cannot equal 1. And I'll explain why in just a second. The logarithm of y with base b is denoted like this. So basically they're saying here that b has to be positive, but it cannot be 1. So it can be a decimal, it can be like 1/2, but it has to be positive and it cannot equal 1. If, that's the positive symbol right there. If it were 1, I wouldn't really have like an actual growth or an actual curve. I'd have a line, wouldn't I? Because 1 to any power is just what? 1. So I'd have a line. So that would change it. It wouldn't actually be a log function. So that's why you cannot have 1. So this is kind of how it works. Log base b of a is equal to x if and only if b to the x is equal to a. And I kind of do like a little loop around. Do you see if you do b to the x equals a? You'll see that b to the x is equal to a. That kind of helps you rewrite it as well. Y'all will get so good at this you don't even need that. But you see b to the x is equal to a. So loop around like this. All right, so let's try some. So write log base 5 of 25 is equal to 2 in exponential form. That is simply 5 squared is equal to 25. Now these are values you know. What about when it comes down to unknowns? You still have to know the relationship and how to rewrite them. So just make sure you understand the base is going to be the base of the exponential, and then the power, which is your, up here the 2 is your power there, raised to the second power. That is going to be the answer to the log. So if you kind of loop around, it kind of takes you 5 squared is 25. You see what I'm doing? And that's how it works. Now the other way, going back the other way, is not quite as simple. So for the other way, I always start with writing log, and then I go to where my base is, and then I still kind of loop around to write it. It's still base 4 of 64 is equal to 3. But you're going to get plenty of practice on this, so you'll get used to doing that. Now, so far we've used various bases and everything, but we're going to learn something called the common log, which is a very common log. There's lots of applications that use a base of 10. We'll eventually learn a log that has a base of e. We'll talk about that very soon too. Okay, so let's go to the next little section. Now, if you see the word log and there's no base written, it is understood that it's a base of 10. So log base 10 is called the common log. If you see a log expression of the form log of n, it is understood to mean log base 10 of n. The log button on the calculator actually is log base 10. Okay, so this button on your calculator you will use eventually. Now let's rewrite in exponential form. So this is just 10 squared. Now this one looks weird, but it's still
10 over 10,000. Now start to think through powers of 10. 10 to the first is 10, 10 to the second is 100. There's a relationship with the number of zeros and the exponent. So if I do 10 squared, I get 2 zeros. 10 cubed, I get 3 zeros. 10 to the fourth, I get 4 zeros. So you should be able to do that pretty quickly. Does everybody understand the relationship I'm making there? See how 10 to the negative 4, it's 10 to the fourth in the denominator. See, I'll have 4 zeros there. That's what I'm saying. There's a relationship there. Okay. At this point, you may have noticed. Wait, I'm sorry, I skipped this section. So this is going to be log base what? 10 of 1,000 is equal to 3. And technically, I don't need the 10. I'm going to keep using it for now until you get used to it. Log base 10 of 1 over 100 is equal to negative 2, because 10 to the negative 2 is 1 over 10 squared. And this is going to be log base 10 of 100,000 is equal to a 5. So 10 to the 5th power would give you 100,000. Is this making sense to you? Okay, now, so that's just kind of converting back and forth. Now we're shifting gears and we're going to start to evaluate. So we're going to evaluate logs. So you're going to need to review all your powers. We'll slowly kind of review in class as well. But so this is saying log base 9 of 6,561. Do you know that off the top of your head? Probably not. You know it's not 9 squared, right? Not 9 cubed. I think 9 to the 4th would work. That's it. Okay? So it's going to be 9 to the 4th is equal to 6,561. So the answer to this is 4. Remember that your answer is always going to be your exponent here. The answer to the log is the exponent from the exponential.
Now, this one's kind of different. I have 5 as my base, and I need to raise that to some power to get 0.2. How can I rewrite this as maybe a fraction? What fraction? Very good, 1/5. And then you can see the relationship. This is going to be a -1 because 5 to the -1 would be 1 over 5 to the first. So this is a time for me to tell you, if you struggle with exponents, you might want to come in for some extra help because I'm kind of assuming you know how to do exponents and use exponents and so forth. So let's go into the next little section. This is just going to be a 4. 10 to the 4th power will give me 10,000. And I am not multiplying a single thing, even in my head. I look at that and I know I have 4 zeros, my exponent is 4. Okay. 4 to what power is going to give me 64? What? 3. Very good. So 4 to the 3rd power is 64. Now this one is not a trick, but 13 to what power is going to give you 1? 0. And it's almost like a little extra property. Log of 1, no matter what the base is always going to be what? 0. Very good. Now, I cannot have a base, like b cannot be 0 and b cannot be 1 for that to be true. But no matter what you're dealing with, it's called the log of 1 property. Basically, log of 1 is always 0. How about this one right here? How do I raise, or what do I raise 4 to get 1 over 16? -2. Very good. Y'all are doing great. Okay. Y'all ready?
Sure.
Okay. I don't want to go too fast, but okay. So, so this is our last little section here. Now, do you notice our unknown is the base here? So the base may be unknown, the power may be unknown, and even like the resulting exponential, like raising to a power, that may be unknown. So any of the 3 locations could be unknown. So here I'm going to do n to the -2 is equal to 1 over 100. So how could I solve that? Do you need to solve it, or do you just kind of already know the answer? That one you kind of should just know the answer. Because if I raise 10 to the -2, it's 1 over 10 squared. So n is 10 here. And usually those, just like this, will be ones where you just kind of know the relationship between the base and the resulting power. Now, this is 2 to the 5th is equal to n. So see how this is a different setup? But 2 is my base to the 5th power. So remember that the result of the log is the power, and that will equal to n. So n is going to be what here? 32, right? Is everybody good with that? So there, the unknown was actually the result of the exponential. So 2 to the 5th is n. That just means n is 32. So here I have 10 to the what power gives me 1,000. Well, that's just n is equal to 3. And you'll get really fast at doing this. Okay, now 5 to the -4th is going to result in n. So n is going to be 1 over 5 to the 4th, which is going to be what? 625. So it's 1 over 625. The next one, n cubed is 729. Now, this one I can actually solve using like a process. So let me show you what I could do. Because my base is unknown here, I could raise both sides to the 1/3 power. I really don't need to do that, but I could. So do you see what happens on the left side? I get n is equal to, and it's the cube root of 729. Which, what do you think that is? Yes, it's 9. Okay, very good. And remember, this will all be without the calculator. So you will review the powers as we practice a lot. And if you need to study them, you obviously can do that too. So 15 to the nth is 225. Okay, interesting. What do you get for that? Just 2. Very good. Just 2. Okay. 4 to some power is 32. 4 squared is 16. 4 cubed is not 32. It's going to be one that I need to manipulate a little bit. So do you remember what we did like 2 days ago, changing to a common base? That's what I'm going to do here, change to a common base. So the left side I'll rewrite with the base of 2. So do y'all get that my common base would be 2 here? So this is from a couple days ago. So I have 2 squared, there's my 4, to the n is equal to 2 to the 5th power. Whoops, not 25, but 2 to the 5th. 2 to the 5th power. So 2n is equal to 5, making n what? We'll just say 5 halves. You go with that? So n is 5 halves. Do you believe me? Like, let me show it to you. If I raise 4 to the 5 halves power, remember when we used to do this? We take the square root of 4 and then we'd raise that to the 5th power. Do you see I get 2 to the 5th, which is 32. So that's how the relationship works. Do y'all have questions so far? Yes, Brandon. You got it? Okay, what about number 8? 16 to the nth is 1/4. So 16 to n is 1/4. I could change to a common base on this one, but y'all should be able to kind of think through this one. How do I turn 16 into 4? I take the square root. But how do I put it in the denominator? I'd raise it to a negative. So n is going to be what? A negative 1/2. Okay, so think about that. Now, if you need to change bases, you can surely do that. So do you understand if I take 16 and raise it to the negative 1/2, I'm really taking the square root of 16, but in the denominator. So that's where the 4 is coming from. Okay, number 9, 81, is that an 81? 81 to the nth power is equal to 27. Now, this is probably a good change of base problem. Okay, 81 and 27 have what base in common? 3. Now, could I use 9? 9 obviously 9 is going to be what? A factor of both of those. But 9 raised to a power doesn't give me, well, I guess I could technically do it that way, but it'd be a little bit harder. So I'm just going to use a base of 3. So how do I rewrite 3 so that it really is 81? To what power? 81 to what power? 3 to what power? 4, right? And then that's to the nth is equal to 3 cubed. So I get 4n is equal to 3. So n will be what? N is just going to be 3/4. Okay, so if I took, first of all, the 4th root of 81, that'd give me a 3. So I take the 4th root. Remember, I always say apply the root first. So take the 4th root of 81, you get 3. Cube that, and you get 27. So a nice feature about this little section is you can check yourself too. Okay, now, what about number 10? How can I rewrite for, like, what is this number right here? 0.04. How do you say that? 4 hundredths, right? So could I just write it as 4 over 100 to start with? I could. Now, so I need to turn 5 with some power into this. What can I do? Could I simplify this a little bit more? And then I might see something. What is 4 over 100? It simplifies to what? 1 over 25. Because that wasn't giving me anything, was it? But that gives me something. I can use that. So 5 to what power gives me 25? Well, that'd be 5 squared, but I have to put it in the denominator. So it's a negative 2. So 5 to the negative 2 is 1 over 25. So you have to take your decimals and convert them to fractions. sometimes you'll need to simplify the fraction, sometimes you won't need to simplify, it just depends. So this is going to be 3 to the n is equal to negative 4. So 3 to some power is equal to negative 4. Any ideas? So if I raise n, or if I make n positive, 3 to a positive is just going to get bigger and bigger and bigger, right? If I raise 3 and I use n as a negative exponent, it's just going to be 1 over 3 to that power. There's no way to do this. You cannot take the log of a negative number because there's no way to raise. Remember what we said to start off with? This base has to be what? Positive. It has to be positive and it can't be 1 because then you just have a line. So the fact that 3 is positive, well, I'm raising it to a power, no matter whether it's a positive or a negative n, I'm never going to get a negative 4, so it's no solution. So you cannot take the log of a negative number. So remember that, that's really important. Now, this is 6 to some power is 0, is 1, I just told you the answer, sorry, is 0. Because remember, log of 1 is always going to be 0. All right. Okay, let me give you the homework worksheet, and you can start on that. And I will set out the answers for you to kind of check, and you can ask questions, that kind of thing.
Why don't we set a goal to maybe finish this in class? I think y'all really can. I really do. It's pretty quick. And then what I want you to do is over the weekend, make sure you're caught up on all your other homework. I was going to check it, but literally there's like 6 people absent today. And I was going to go over all of it. But I want to save that maybe and make sure you know exactly what your questions are on Monday. So that's going to be our plan. Finish this right now. Set a goal. Finish it in class as much as possible. And then we will go over all the other homework and all the other, I'll show you what they look like. Right here. So you need to make sure you know all this information is here. Okay? There's plenty of notes, videos, the answers will be up there for everything except for today's lesson. So you can check all your answers. Is everyone able to get to the website or to Blackboard, one or the other? Okay, because there were some issues with that.